Let's look at classifying different types of chemical reactions that you can have. This first way to classify chemical reactions is different from the one listed in your text, but it's one that students tend to have an easier time with, so I wanted to take a look at it. If you have more than one starting material becoming just one product, that is a combination. They're coming together. If, on the other hand, one starting material is becoming more than one product, that is decomposition, breaking apart. And these are easy to recognize because we have a different number of starting material and product. We have 2 going to 1 or 1 going to 2. The other types of reactions, unfortunately, don't all fit on one page. The other types of reactions all have 2 things going to 2 things. So 2 things going to 2 things here, and even there with combustion. So if you have 2 things going to 2 things, you know you can't have combination or decomposition. The next thing to take a look at is combustion. Combustion is some sort of fuel combining with oxygen gas to become carbon dioxide and water. So it's a very specific reaction. If you don't have all of those components, it's not combustion. If you've eliminated that possibility, then you need to decide between double displacement and single displacement. Single displacement, we have an element and a compound becoming a different element and compound. So this B has jumped into the compound and replaced one of these components. If B is a metal, it's going to replace the metal. So here we have an ionic compound. C would be the metal, D would be the non-metal. So if B is a metal, it's going to replace the metal. So you get a compound like BD. If B is a non-metal, it can replace the non-metal. So then you'd get a compound like CB. If you start with 2 compounds instead of a compound and an element, they can just switch partners, and that would be a double displacement. Let's take a look and see if we can classify these reactions. For this first one, we have one starting material becoming more than one product. It's breaking apart. This is a decomposition. Here we have 2 things going to 2 things. It's not a decomposition or a combination. It's also not combustion. So we are deciding between single displacement and double displacement. Since we have an element and a compound becoming a different element and compound, this is a single displacement. The zinc is displacing the copper. So this reaction has 2 things going to 2 things, so it's not a combination or decomposition. This one we do have a fuel and oxygen going to carbon dioxide and water, so this is our combustion reaction. Here we have 2 things going to 2 things, and it's not a combustion, so we're deciding between single and double displacement. Since both of these things are compounds and they are switching partners, this is a double displacement. And this last reaction over here, we have 1 thing going to 2 things, and so right away we know this is a decomposition. The 2 things that it does become happen to be carbon dioxide and water, but this is not a combustion reaction because we do not have a fuel and oxygen as our starting materials. This is a decomposition reaction. So the 3 types of classification that your textbook uses are precipitation, acid-base, and oxidation-reduction reactions. Precipitation and acid-base are 2 types of double displacement reactions that we're going to take a closer look at. And then oxidation and reduction we're just going to look at sort of as something that can take place within a reaction. And it can take place in a combination reaction, a decomposition reaction. Combustion reaction definitely has oxidation reduction taking place. Single displacement also has oxidation reduction taking place. So all these other 4 that we have looked at can have oxidation and reduction as a part of them. So let's spend the rest of this lecture looking at precipitation and acid-base, and then I think I will do oxidation and reduction as a part 2 of lecture 4.2. All right, I think that looking at these as double displacement reactions makes it a little bit easier to come up with the products. Let's go ahead and separate these compounds into the ions that they could have in them, and then we'll switch the partners and come up with the results for these acid-base reactions. All right, so I've separated these partners. If we want to swap partners, it's better to separate them first, so then we can do a swap. Let's see what partner lithium is going to end up with. So lithium can partner with cyanide ion, but it already started that way, so that wouldn't be a swap. So let's not do that one. Lithium cannot partner with hydrogen because they're both positive. That would not make a neutral compound. So lithium has to partner with the nitrite ion. So one of our products could be lithium nitrite. And let's make sure we write the formula correctly with balanced charges. One of each is okay, so here we have lithium nitrite. And then what's left is the hydrogen pairing with the cyanide. The cation is always written first. So this is the proper formula for hydrocyanic acid. Okay, and we can do a quick check to make sure that they are balanced, the elements. One lithium on each side, one cyanide ion on each side, one hydrogen, and one nitrite. So we don't need to change the coefficients. The only thing we need to do is add the state. They are dissolved in water, they're soluble, so we can put aqueous for both of them. So we have completed this reaction. Let's try doing a partner swap on this one. First we separate the partners so we could do the swap. All right, I have separated the partners. I did not put the 2 in front of the hydroxide or the hydrogen ion like I would if this were a complete ionic equation. I'm just more concerned with the identity of what these ions are, and then I'll balance it after we've come up with the correct products. All right, so magnesium could pair with hydroxide, but that would just be the same thing. It wouldn't be a swap. It cannot pair with hydrogen because they're both positive, and so it will pair with sulfate. Let's get the correct formula for that. Magnesium sulfate. And now we will go ahead and pair the remaining, the hydrogen and the hydroxide together. So hydrogen and hydroxide together is actually how you make water. So the correct way to write that formula would be H2O. So the magnesium sulfate is dissolved in water. We will write this as aqueous. Water itself, we don't really say that water is dissolved in water. This water would just be part of the liquid that is in our reaction container. And now the next thing to do is to balance this equation. All right, to make this easier to balance, I went back and drew the fact that we have 2 of these hydroxide ions and 2 of the hydrogen ions. So when we combine these, we are actually going to get 2 water molecules when we combine it. And then if you go through at this point, the reaction is completely balanced. Okay, so let's do this double displacement partner swapping with these precipitation reactions. What's happening in a precipitation reaction is that 2 soluble compounds are being mixed together, solutions of them are being mixed together, and then the compounds that end up forming, one of them is not soluble. It's a precipitate that undissolves from the solution when you mix them together. And that is the driving force for the reaction. So again, if we're going to swap partners, we need to separate them first. So I've separated the partners. Now I'm going to try to swap them. Hydroxide is something that potassium had to begin with, so that would not be a swap. Zinc is positive, so it would not combine with the potassium. So we can make potassium chloride as one of our products. And then the hydroxide would end up with the zinc, but we just have to write the cation first. And the correct formula for zinc hydroxide would have 2 hydroxide ions in it because zinc is a +2. Now that we have the correct formulas, we can balance the equation. Alright, and what I'm noticing first is that there is more oxygen and hydrogen on the right side. So I'm going to go ahead and increase this so that I can get more oxygen and hydrogen on the left side. And the potassium gets increased also. So now the potassium and the chlorine are too high on the left, so we need to increase them on the right. And now we have all of the elements balanced. The last thing we have to do here is include the state. We have to tell whether this is aqueous, which is dissolved, or is it the solid precipitate, which is not dissolved. If something is dissolved, it is soluble. So if it's soluble, it means that it can dissolve. And if our compound is soluble, we will label it as AQ, aqueous. If something is not soluble, then it is not dissolved, and that will be our solid precipitate. Some people get a little bit confused because S stands for solid, not soluble. So don't get confused with that. If something's soluble, it will be aqueous. If something's not soluble, it would be S for solid. So how do we know if something is soluble or not? Let's take a look at our solubility rules. A little bit lower down here, we have a solubility rules table. So the way that we read this table is that we have certain things that are generally soluble. Included in that are group 1 metals and ammonium ions. So these are generally soluble, and the exceptions to that are none. So this kind of matches what this is. So there are no exceptions. Anything with a group metal cation or ammonium as the cation will be soluble with no exceptions. Halides, something with a halogen as the anion like chloride or bromide, is also generally soluble. However, this time we do have some exceptions. Silver halides, mercury 1 halides, lead 2 halides, they are not soluble. They're an exception to the solubility. Some other ions that are soluble, acetate, bicarbonate, chlorate, and nitrate, and these have no exceptions. And then sulfate ion is generally soluble, but sulfate does have a few cations that are exceptions. So these are kind of matching line by line here. Then we have some things that are generally insoluble: carbonate, chromate, phosphate, and sulfide. The exception here is if it's a group 1 metal, because remember, group 1 metals or ammonium are always soluble with no exceptions. And so if they are involved, these will be soluble, otherwise they generally won't be. Another generally insoluble thing is hydroxide ion, unless, of course, we have the group 1 metal again, which is a soluble compound, and also barium hydroxide is fairly soluble. All right, so let's go back to our problem here. This first compound is a group 1 metal, which is generally soluble, and a halide, which is generally soluble. And so this one is soluble. We're going to write this as aqueous. It's dissolved in the water. Hydroxide is generally insoluble unless it's paired with a group 1 metal. Zinc is not a group 1 metal, and so this would be our solid precipitate. This one's not soluble. It's insoluble, so we have a solid precipitate. Okay, got a couple more examples to try to do. First, we'll separate the partners. All right, they have been separated. Calcium is already with nitrate, so that would not be a swap. It can't be with sodium because they're both positive, so it will be with carbonate. The correct formula is CaCO3. We have 1 plus 2 calcium combining with 1 minus 2 carbonate. That leaves sodium to be paired with nitrate. The correct formula for sodium nitrate is NaNO3. Some people might be tempted because they see 2 sodium and 2 nitrate to write NaNO3 2, but this is not the correct formula for the compound. We have sodium with a +1, nitrate with a -1. We just have one of each. So this is the correct formula. All right, but the fact remains that we do have 2 sodium and 2 nitrate. So let's go ahead and balance that. So since we do have 2 sodium and 2 nitrate, it's not balanced if we just leave one of each on both sides of the equation. And so we can take care of that though by putting a 2 in front here. That will increase the nitrate and the sodium to the numbers that we need. So instead of writing Na2NO3 2, which is incorrect, we just write 2 of the NaNO3. Now the last thing we have to do here is determine which is soluble and which is not soluble. The carbonate is one of our generally insoluble ions. So the carbonate is one of our generally insoluble ions unless it's with a group 1 metal or ammonium. Calcium is not one of those, so calcium carbonate would be insoluble. And then our other product, sodium nitrate, we have sodium and nitrate, both of which are soluble with no exception. So sodium nitrate is definitely soluble, however you look at it. The insoluble calcium carbonate is the one that we label solid. That is our solid precipitate. The soluble sodium nitrate is our aqueous compound. All right, let's do this last example, separating the partners so we can swap them. All right, now that they're separated, let's give lead its new partner. Nitrate can't be its new partner, that was the old partner. Sodium can't be the new partner because they're both cations, so we have lead-2 sulfate. And that would be the proper formula for lead-2 sulfate. That leaves sodium to pair with nitrate. And this is the proper formula for sodium nitrate. So originally we have 1 lead, 2 nitrate, 2 sodium, and 1 sulfate. So making 1 lead sulfate works out. The 2 sodium and 2 nitrate will end up making 2 of the sodium nitrate. So I just did a kind of a shortcut to balance that. And now the last thing is to figure out which one is a solid and which one is dissolved in solution. And sulfate is generally soluble except with lead-2. So this is not soluble. This is going to be a solid precipitate. Group 1 metals and nitrates are soluble with no exceptions, so this is definitely dissolved in aqueous solution.